Welcome to the lecture series on probability theory and stochastic process. In this lecture, we talk about channel capacity. Earlier, you have gained much knowledge about what is amount of information, what is average information or entropy, and then what is information rate. These three parameters characterize the behavior of an information source. Generally, information source consists of a particular source alphabet consisting of finite set of symbols. When this information source is generating messages, how much amount of information is contained by kth symbol is ik. Whereas H, the entropy is mainly focusing on long sequence of messages. When there exists a long sequence of messages containing number of symbols, what is the amount of information on average contained is entropy. Then information rate is going to describe how much amount of information generated per second. These three fundamentally are meant for describing the behavior of information source. Then, even though information source is ready to generate information, it cannot generate as much information as it can, because the capacity of the channel, how much information the channel can be able to transmit or propagate through, is very important. This term is mentioned as channel capacity. Channel capacity is very important in digital communication system, as it is going to put a constraint or a bound on the amount of information that is to be transmitted over the channel. This is because it is not necessary that all the information generated by the source will be effectively transmitted over the channel, because every channel has certain limitation. It cannot transmit whatever information that has been transmitted. This is defined as channel capacity. It can also be given as the maximum amount of information. Channel capacity can also be defined as the maximum amount of information that can be transmitted or transferred over the channel by the information source. This is the expression for channel capacity. I of xm equal by, we know it is called as a mutual information. Mutual information is defined as the amount of information transferred when symbol xi is transmitted and yj is received. That is mutual information. So how much maximum amount of information transmitted, that is given as a channel capacity. This channel capacity is going to be putting a limit on the capacity of the information source. The Shannon's channel capacity theorem, the Shannon's channel capacity theorem is going to put a constraint on the information source. It states, how it is given in terms of mathematical expression. It is given as capital R, that is information rate always, capital R should always be less than or equals to C. This is the mathematical expression for Shanon channel capacity theorem. What it states: when there exist capital M mutually exclusive symbols that are generated by an information source, then these symbols can be transmitted over the channel with minimum probability of error if this condition is satisfied. This is called as Shannon's channel capacity theorem. We know what is R. R is information rate. R is information rate. What is C? C is channel capacity. Okay, so the information rate should never be larger than the channel capacity as given by Shanon. What happens if this information rate exceeds the channel capacity? What happens is nothing special. The information cannot be transmitted with a reduced probability of error. The receiver may not be able to get the exact information what it is required to. This is known as Shannon's channel capacity theorem. Shannon has also defined that this channel capacity is going to be depend on two parameters. One is called bandwidth and second one is signal to noise ratio. So according to Shannon-Hartley law, also called as Shannon-Hartley theorem, the this is channel capacity. Okay, according to Shannon-Hartley law or Shannon-Hartley theorem, channel capacity is given as capital C equal to capital B into log base 2 of 1 plus S by N. What are these parameters all corresponds to? Capital C is the channel capacity. Okay, C is channel capacity and B is the bandwidth. Okay, we know what is bandwidth. Bandwidth is a range of frequencies occupied by a signal. Sn. It is defined as signal to noise ratio. Signal to noise ratio. It is the ratio of average signal power to average noise power. Okay, so this is Shannon-Hartley law, which is going to put a constraint on the bandwidth and signal to noise ratio for a given communication system. So generally we have already we have discussed, we have mentioned that channel capacity must be maximum, right? So C, what is C? C equals to maximum amount of information that can be transmitted. So what is our objective? C must be larger, right? Channel capacity should always be larger, no? Maximum information must be transmitted over the channel. In this case, there are two conditions. First one is either make bandwidth larger, first one, or second one, or have a signal to noise ratio larger. These are the two possibilities that one can have to increase channel capacity, right? So if I want to have channel capacity, for example, say I want channel capacity infinity or maximum, say for example, case number one, case one. What I do? I will make bandwidth very larger. Bandwidth is very larger. But however, if the bandwidth is very larger, automatically in such a case, it introduces noise in the system, in the signal. If bandwidth is very larger, I just take small example to make you better understand. If one can be able to receive all frequency components, what happens? Imagine a scenario. Because we know now what is the audible frequency range. Audible frequency range is from 20 hertz to 20 kilohertz. This is the audible frequency range. Generally, anybody is able to listen. But if this audible frequency range is much increased, say, if this audible frequency range is much increased, what happens? You can be able to listen all signals, right? You can be able to listen all signals. What happens then? A much disturbance. You can be able to listen any voice on the earth, any creature's voice. Then noise, right? So case 1 failures. What is case 1? Increasing the bandwidth, okay, bandwidth rise to enhance channel capacity, to enhance channel capacity is not advisable, is not possible, unadvisable also, whatever. Why? Because why not advisable? Because rise in bandwidth increases noise. Rise in bandwidth increases noise. So this possibility is ruled out. Then what is the another case? Another case is have signal to noise ratio very large. Case 2, have signal to noise ratio very large. This is accepted. But how can I have signal to noise ratio very large? If I assume, if channel is ideal, then SNR value larger, so capacity larger. That is why Shanon says, for a Gaussian channel with white noise and the channel is ideal, that is noise free, signal to noise ratio is infinity. Once signal to noise ratio is very larger, automatically channel capacity also will be larger, right? But there is no channel, having zero noise. We can never, irrespective of so many generations of communication technology, 1G, 2G, 3G, 4G, 5G, etc., till now, the noise cannot be completely removed. So what is the possibility there? So case 1, bandwidth equals to infinity, not possible. Case 2, signal to noise ratio equal to infinity, not possible. So in such a case, how to increase the channel capacity? In such a case, how to increase? Because we know channel capacity is given as C equals to B log base to 1 plus S by N. So what we can do is fix a specific amount of bandwidth, correspondingly increase signal to noise ratio to some value. Okay, to have a constant channel capacity, bandwidth can be fixed and thereof you can modify signal to noise ratio. Okay, first possibility, fix bandwidth and rise SNR. Okay, second one, what is second possibility? Fix signal to noise ratio and rise bandwidth. Because bandwidth, I repeat again, bandwidth is defined as the range of frequencies occupied. So these are the two parameters that can be adjusted to have a constant channel capacity. This is called as bandwidth, signal to noise ratio trade-off. Signal to noise ratio trade-off. So what is the meaning of trade-off? You compromise between either the bandwidth or signal to noise ratio so that you can get the required channel capacity. This is called as Shanon-Hartley theorem or simply Shanon-Hartley law, which I again mentioned. Capital C equals to capital B log base to 1 plus S by N. Don't forget the units for channel capacity are bits per second, because it is the maximum amount of information, no? So the units for this are bits per second. Further, We can do some mathematical analysis over this. So what I do, I take bandwidth as B and I am measuring my measured noise power in the bandwidth B N naught. Some Taban Schilling has taken it as eta, no issue, you can take any value. I have multiplied and divided with S by N. So in such a case, it will be equals to log base to 1 plus S by N naught into B. Why N naught into B here? Because I am measuring the bandwidth, I am measuring the noise power in the bandwidth B. So if I simplify further this equation, what happens? Let us see. So this will be S by N naught. S is the signal power, right? And N naught is the noise power measured over the bandwidth log base to 1 plus S by N naught B. Okay. I modify again. This can be written as being a logarithm S by N naught into log base to 1 plus S by N naught B into 1 over S by N naught B. From the logarithmic fundamentals, you can write this as x tends to 0, 1 plus x power 1 by x equals to e. So the previous equation, let me rewrite. C equals to S by N naught log base to 1 plus S by N naught B into 1 over S by N naught B. This will become S C equals to S by N naught log 2 base E by using the above mathematical expression. So what happens? This will be around 1.44 S by N naught. So if you proceed in this manner, you can be able to see channel capacity in turn proportional to 1.44 times signal to noise ratio. Thus, even though the information source with its source alphabet, entropy and information rate able to send the information over the channel, ultimately the channel capacity is the parameter which decides with this much of rate only the information can be transmitted. Otherwise, there will be a probability of error more in the information transmitted. Remember forever, in communication, simply the transmitter sending the information is not sufficient. The other side of that one, the channel must be able to propagate that, and same time the receiver must be able to decode it. That is why Shanon has defined these two theorems for effective information transmission. That is about in this lecture. In next lecture, we discuss more about source coding techniques and different types of source coding. Thank you.